Hello, in this video I'm going to be discussing the reflection coefficient in a transmission line whenever the reflection coefficient becomes frequency dependent. So what that means is that we basically have a source impedance and or a load impedance that is dependent on the frequency of the wave traveling through the line. So here we have a setup for a DDR2 interface. So I pulled these from a transmitter, you would have to do it for both ways, but you would have to do it for the IBIS model being the source for the transmitter, and then like the computer, like a microprocessor, and then you would have to do it for a load being the DDR2 chip, and then you'd have to do it in reverse, where this is the source and this is the load. So basically the pulse is chosen to be the DDR2, and I assumed that the rise and fall times were 10% of the period, and that the on would just be the difference. But so what we'll do is we'll do a simulation. So pretty much, if I haven't stated already, these right here and right here model the IBIS models. So these parasitics right here and these parasitics right here come from the IBIS models. You can't really choose to get rid of these unless you went with something like a bare die. So what that would be, because these model the bond wires and that connect the die to the pin on the chip, and if you get rid of the package and you use a bare die, you can get rid of these, and perhaps it'll help your not only signal integrity but power integrity. And that's possibly the reason that they do it with microprocessors. So when you buy a microprocessor, it's on this little PCB, and then there's the bare die, and then there's capacitors all over it. And they do that for possibly two reasons: because the speeds are so high that it actually makes it easier for them to design the chip interface for signal integrity, and then it makes it easier to decouple the power. So the thing that I'm going to be discussing today is basically we have a input that, if I can get this. So we have this little pulse, right? And when it comes down, it'll arrive and it looks really degraded. But what I'm going to be discussing today is the reflection. So pretty much, since the pulse here has frequency content, so if you did the Fourier transform, you would find that it has all this different frequency content, and these reflection coefficients will be frequency dependent. So what you'll get is what will actually happen is that the reflection coefficient will act as a high pass filter. So the low frequency content of this pulse will be terminated more so than the high frequency content. And if you go into the very large harmonics, what will happen is that the energy just seems to bounce around back and forth almost indefinitely, and the only way that it attenuates is through the lossiness of the line. So we can look at the very far out there. So you can see that these right here look pretty much the same, but you see that it kind of attenuates, but it most certainly isn't terminated. But we can look, because you still have this stuff. And the maximum noise for reflections would be whenever all these stack up so that they create a big spike in the positive and a big spike in the negative. So you would want to use the most lossy material that you possibly could, because then it reduces this noise, unless it reduces the main signal too much, because you would have a trade-off. So a lossy material dampens all these reflections that aren't terminated because of the IBIS model. But if you do choose a lossy material, then this main peak may be attenuated too much. And I believe that's all I wanted to share.